who, despite having the same last name as me, is not actually a relative of mine. But he is a friend who I've known for a very long time. In fact, he and I wrote our very first computer program together about almost 30 years ago now. It was an adventure game written in BASIC. After that, Waddy went on to college. Even when he was in high school, he worked for Thinking Machines Corporation, producers of the Connection Machine, and he worked for them again after college. But then, unfortunately, the intellectual rigor and complex math of computer programming became too much for him, and he moved over into theoretical physics. He's now a professor at MIT at the Center for Theoretical Physics. And we've lost our screen. Well, he's here to talk about how big the universe is, which for Google means how many data centers we're going to need. So please welcome Professor Washington Taylor.
Great. Thank you very much, Ian. And thanks to Ian and the seminar organizers for inviting me here. It's a pleasure to be here. I'm very pleased that so many of you can come to a talk which is probably going to be about as far from practical application as most talks, as any talk you might have heard here. So what I'm going to talk about today is a story which has emerged in recent physics having to do with how big the universe is and how we're going to make predictions about future experiments, things that will be seen at accelerators that are not yet built, things that will be seen in cosmology, in the context of a rather challenging worldview which has come out of string theory and cosmology in the last few years. So I'm going to start off a little shift to the left. Is there any way to fix that?
The image on the screen is a little off.
Well, I'll carry on. So let me just summarize most of the big picture in a few words, and then I'll get into a little more of the details of this and how this turns into what could be a very difficult computational problem. So recent evidence coming from two different directions. On the one hand, from cosmological experiments, which measure things that happened at the in the very early history of the universe that we see at very far distances away from us, 14 billion light years away. These observations have combined with some recent theoretical developments in string theory to give us a picture of the universe which is radically different from that which we had in the past. It's sort of the next step in a Copernican revolution, wherein our little patch, 13 or 14 billion light years wide, of the observable universe seems to be potentially part of a much, much, much larger system. And in other regions of this much larger universe, going beyond the horizon to which we can see with our experimental apparatus, there may be regions in which the physics is governed by somewhat different laws, and in some places there may be regions where the laws of physics look very different, all governed in some sense by an underlying theory, which perhaps is string theory, but from the point of view of traditional particle physics, these different regions in the universe may have very different kinds of physics. So one of the challenges in this picture, where the universe is so big and physics is different in different patches of the universe, is making predictions. So in some places in the universe, physics may be very, very different from ours, and there may be some places in the universe where everything is almost exactly like it is here, but if you look at the electron mass, the 9th digit of the electron mass may be off by 1. And if that is in fact the case, it means that that 9th digit of the electron mass is not something we can predict based on fundamental physical theory. So the title of the talk is, When is a Googol Not Enough? And I'm sure each of you at some point since coming here or before coming here has gotten into some discussion about how big the number of Googol really is. And as you all I'm sure know, a Googol is pretty much bigger than anything you could run into in almost any physical problem or any problem of relevance to nature, because a Googol is approximately the number of particles in the observable universe. So you might think that you will not need to deal with numbers or computational problems, well, obviously some computational problems search exponentially big spaces, so you might need to search combinatorial spaces of that size. But you certainly wouldn't expect to see this number appearing in a characterization of a physical system. The point of this talk is that in this new picture of the universe, it seems like there may be far more than a Googol different regions of the universe, each with their own laws of physics. String theory, in particular, seems to have more than 10 to the 1,000 different solutions, each of which corresponds to some kind of local physics. And if the current paradigm that is emerging is correct, each of those may be realized somewhere in the universe. This poses a huge computational problem. Even if we can, in principle, completely understand string theory, even if we could define it, write down the equations, and even solve those equations, how would we sort through this 10 to the 1,000 or more possible solutions to find the one that matches our world? And so what I want to talk about today is filling in a bit more as to why we ended up at this picture, telling you about how to think about the problem of making some prediction based on this model, and then talking a little bit about some of the computational problems. I and some other people have been working on actually starting to systematically look at this space of solutions and trying to understand if there are correlations, if there are structure, if there are things we can do which make this into a computationally tractable problem. So I'll talk about some of that. I encourage questions from the audience during the talk. Yes? So the question is, could each of these solutions be realized just once? No, as we'll see as we get through the story, probably each of these solutions is realized many, many times. So the size of the universe is probably much bigger than this, if this picture is correct. You could take the currently observed size of 13.5 billion light years, you could tack on pretty much as many zeros as you want after that, and you might still not be quite approaching the size of the space-time that you would need to capture all the physics that might be realized. Now I'll talk a little bit about how things got so big, why the universe might be so big as we go through this. But yeah, I encourage questions as we go through. I'm going to kind of try to keep this to a fairly simple and straightforward core of what I'm talking about, but there's lots of things I'm going to kind of gloss over, and if people are interested, I'm happy to say a little more about anything. Okay, so here's a quick outline of what I'm going to talk about. I'll start by discussing the idea of cosmological expansion, how the universe got to be so big, and some issues which have to do with recent cosmological observation, telling us about the rate of expansion of the universe. Then I will talk about string theory, which is a formal development, a theoretical framework in which people have been trying to describe quantum gravity. And then I'll bring them together to talk about the vacuum problem, the problem of looking at these many solutions of string theory and figuring out which one might correspond to our world. Finally, I'll talk about the computational challenge that appears when we have this huge space of solutions. Okay, so let's start with cosmic expansion. So the basic feature of gravity, which makes it different from all the other forces, is that all objects exert a gravitational attraction on all other objects. That's not true of electromagnetism. If you have two positively charged particles, they will repel each other. If you have oppositely charged particles, they will attract. In gravity, everything attracts. So, although gravity is by far the weakest of all the forces in nature, this fact that it is a universally attractive force is really what makes it such a relevant force in our everyday lives, because we're interacting with big objects, the sun, the earth. These things all have lots of mass, and they attract us, and they attract each other, and cause most of Newtonian gravitational physics to happen. So, in the absence of any other effects, if you have a bunch of objects floating around in the universe, they will gravitationally attract each other, and they will begin to come together. So one consequence of that observation is that we can't have a static universe if the only force between these objects is gravity. If you just try to populate the universe with a bunch of objects and keep them at fixed points, they'll all attract, and things will come together. There'll be some kind of collapse. So about a century ago, Einstein was worried about... Yes, please, question. That's a good idea. Great. Yeah, it's a little smaller, but that's probably much... Yeah, let's do that. Thank you for that suggestion. Okay. So about a century ago, Einstein worried about this, and Einstein wrote down this beautiful theory of general relativity. The basic equation of general relativity is there's a thing called G mu nu, which characterizes the curvature of space-time. And there's a thing on the right called T mu nu, which characterizes the amount of matter and energy that's moving around in that space-time. And he had this beautiful and simple equation, G mu nu equals 8 pi T mu nu. I promise I won't have very many equations, but this is one of the very few I will include. He had this beautiful equation saying that gravity is caused by matter. You have matter, it causes space-time to curve. And in turn, the curvature of space-time causes things to move on curved trajectories. And that explains all of gravity. But he couldn't explain why things weren't all collapsing together. So he stuck in a fudge factor, a little extra term in this equation, which is that thing in blue over on the right. He added a little g mu nu, which is describing, that's called a metric. It describes distance scales in space-time, multiplied by a constant called capital lambda. So capital lambda is something called a cosmological constant, and he stuck it in basically to allow his theory of general relativity to have a static solution, a solution where all the stars were fixed in the heavens and they weren't coming towards each other and they weren't going apart. Well, Hubble pointed out, after some observations, that in fact, it seems that the universe is expanding. All objects are moving apart from all other objects at a fairly rapid rate. And what that means is that we're not in a static universe. And Einstein said, oops. And he characterized the addition of this term into this equation as his greatest mistake in his career. Because he said, we don't need it, we can get rid of it. Basically, we have the universe expanding, and gravity will just cause the rate of expansion of the universe to gradually decrease as the objects attract each other. So ever since then, people have basically believed that this thing, the cosmological constant, is zero. You set it equal to zero, the universe expands, there was some big bang, the rate of expansion gradually decreases as gravity pulls everything together, and that people thought was the end of the story. Now, in the last few years, people have done very careful observations of distant supernovas, of the large-scale structure of microwave radiation left over from just after the Big Bang, a lot of detailed cosmological observations. And what those things tell us is that the rate at which the universe is expanding is no longer decreasing. It's actually starting to accelerate. So distant objects, you would have thought gravity would just slow down their rate of motion away from each other. Distant objects are now starting to accelerate away from us at a faster and faster rate. So this implies that the cosmological constant is not, in fact, zero. What the cosmological constant does is it sort of exerts a constant pressure of everything on everything else, which causes things to expand. It can be characterized as a kind of a dark energy, an energy which cannot be measured in any particular way, but which seems to be causing things to move apart. So it now seems, and there's pretty convincing evidence for this, that for about 7.5 billion years, about half the lifetime of our universe, of our local patch of the universe, the rate of expansion has been increasing. Things have been moving apart from each other faster and faster. And this is now a big puzzle in cosmology. You might have seen discussions in some popular science or more technical things on dark energy. This is the issue, that we now think that much of the energy in the universe is made up of this dark energy, which is forcing everything to accelerate apart. So if you characterize the amount of this dark energy, this stuff which is causing the rate of expansion to increase, the thing which Einstein thought was a blunder but in fact seems to be there, if you characterize the amount of that stuff in natural units, which you can sort of make everything dimensionless so you end up with a dimensionless number, the number describing the cosmological constant seems to be about 0.00, and there's 119 zeros, and then there's a 1. So it's 10 to the minus 120. It's an incredibly small number. So somehow, the universe is very finely tuned so that for a long time it was expanding under the influence of the initial energy causing the Big Bang, and things were slowing down. And then only very late in the history of the universe, after galaxies had formed and lots of structure was here, has this cosmological constant taken over and forced things to start moving apart faster and faster. Okay. So that's the cosmological observation. It seems that the universe is expanding, but the thing causing it to expand is an incredibly finely tuned number. And from basic physics, it's not obvious why this number should be so finely tuned. Any questions about that? Okay. So let me come to a slightly different aspect of this story, another set of cosmological observations, which also tell us about some expansion, but in a slightly different context. So there was a thing called the Wilkinson microwave anisotropy probe, which went up in space and was very carefully measuring the microwave radiation coming from the very early universe, coming from different directions. You might have seen pictures of that also if you read some popular science things. According to those measurements, there's an incredible similarity between patches of the universe in different directions in the sky. And what that means physically is that it seems like those regions must have somehow been in causal contact. Things that happened in one of those places that we see at the very far distance must have influenced others. But according to a simple model of the expansion of the universe and the history of the universe, there's no time in history when those things would have been in causal contact, because the light from those two things, those two different directions, is just now meeting us. So if you have light rays coming from 2 points coming together and just now meeting us, it's very hard for a light ray from one of those to have gotten to the other in the far distant past of the universe. So people found this very puzzling, but there's a nice, simple, and beautiful explanation for this, which is the notion of inflation, which a fellow named Alan Guth, who's now at MIT, came up with. The idea of inflation is that in the very early universe, probably even before the Big Bang, there may have been a significantly large cosmological constant. And that large cosmological constant, as we've discussed now, causes the universe to expand. And if that number is not 10 to the minus 120, but a half in natural units, then it causes the universe to expand very quickly. In every Planck unit of time, the size of the universe will multiply by a factor of e. So you rapidly get exponential growth. And like stock markets, until they undergo corrections, it would just get bigger and bigger and bigger, faster and faster, until some correction would kick in and move us into the phase of the universe we're now in at this time. So the scale of the universe in that period of expansion would go as an exponential in time. Now, we do not now live in a universe which is incredibly rapidly inflating. So there was an initial picture of inflation, which Guth came up with, which I will describe here because it's relevant to the later part of this story. And we can combine the two things we've talked about, that in the distant history, the cosmological constant was bigger, and now it's incredibly small, in this little picture where we have some kind of a potential function, sort of a landscape, where there's one minimum of this potential at a high value. So it might be that the universe used to be living in this red dot, vacuum 1, where the cosmological constant was fairly high, and things were inflating very rapidly. And in quantum mechanics, in classical mechanics, if you're in a local hill valley like that, you'll never get out of it. But in quantum mechanics, you have a wave function which can kind of creep out over the hill, and suddenly you can sneak out. It's true. I was told I didn't want to move too far away from the microphone because then nobody will hear me. So if we move down into the green minimum, by quantum tunneling, we get a wave function which sort of moves out of the first vacuum into the second vacuum. At a certain point, we can suddenly get a region, a bubble of this second vacuum popping out, and we would move into, by quantum tunneling, the vacuum that we now live in with a much smaller cosmological constant. So let's just keep that picture in mind. This is one scenario for how we could get a very high cosmological constant in the past and a smaller one in the present. This scenario, as described, can't be exactly right. This is the old version of inflation, and there's some newer ideas which are taken into account. But this is actually more relevant for the story I'm telling today. Yes, question? Yeah, I'm actually talking about the whole universe, or a region in the universe. So here's the way to think about it. If we live in a situation where everywhere in the universe we're in vacuum 1, what can happen through quantum tunneling is a patch of a certain size can creep into vacuum 2. And if that patch is big enough, that patch will take over. Well, what it'll do is it'll form a bubble. And that bubble will expand on its own, under its own cosmological constant. It'll expand at the speed of light. The region outside it will also be expanding. And I'll come to a picture in a little bit where you'll see what the universe starts to look like. You get a background where the universe has a large domain in region 1 with a bubble inside it in domain 2, in vacuum 2, and both of them are expanding. So each one of them is getting bigger and bigger over time due to its own cosmological constant. Yes, another question. Good. So the question is there anything which rules out negative matter, something which would cause a repulsive force in gravity? So there have been a lot of experiments testing gravity in great detail and looking for so-called fifth forces, which would be additional forces which might be interpreted as negative gravitational forces. So far, none of those experiments have come up with anything definitive. There are alternatives to Einstein's theory of general relativity. None of them are, in my mind, at this time, equally attractive as explanations of what we see in nature. But there are some puzzles having to do with both dark energy and a more prosaic kind of dark matter, which is extra material that seems to be in the universe. These detailed observations by WMAP tell us that only a small fraction, less than 10% of the matter in the universe, or the energy in the universe, is the stuff we can see, baryons and the stuff that makes us up. Some fraction of it is made out of dark matter, which is some kind of matter we can't yet observe, and some part of it is made out of this dark energy. And there are alternatives to Einstein's general relativity. One in particular is called MOND, which modified Newtonian dynamics, which purport to give an alternative explanation. I would say at this point in time, these are on the fringe of what's widely accepted. It's pretty uncontroversial that most experiments very strongly support Einstein's theory of general relativity, which would give us a picture where the mass that appears in the term sourcing the gravitational field is the same as the thing which is affected by the gravitational field, and that just always gives you an attractive force. Good question, though. Other questions? Okay, so we've talked a little about cosmology. Next, I want to move to string theory. So what is string theory and why would I want to talk about it? So there are four forces in nature that we have observed and verified with clear experiments. There's electromagnetism, which we're all very familiar with. It underlies all our electronics. There's the strong and the weak nuclear forces, which are equally important. The strong nuclear force holds together the charged particles in the nuclei of atoms, and the weak nuclear force is also relevant in nuclear interactions. And then finally, there's gravity. As we've said, gravity is the weakest of these forces, but the only one which is universally attractive. Now, we have this really snazzy mathematical framework for describing theories of forces. It combines quantum mechanics with field theories like electromagnetism. It's called quantum field theory, and it's a very elegant theory. It accurately describes three of these forces. It describes electromagnetism, the strong, and the weak nuclear forces. But if you try to use quantum field theory to describe gravity, you run into significant problems. All kinds of hell breaks loose, and you really can't make sense of what you've got. The issue is essentially that in quantum mechanics, you are looking at all possible ways that a system might fluctuate or make a trajectory from one point to another in its space of possible configurations. And in the case of quantum field theories, that means you imagine that a particle could take all possible routes to get from A to B, and then you sum something over all of them. In the case of gravity, that means that you have to sum over all possible ways that space-time itself could fluctuate, and that would include things like little wormholes appearing and disappearing, and very complicated things happening with the geometry and topology, which we don't have any mathematics to really handle. So there's some foundational level at which we don't have the right mathematics to do it, and there's sort of a practical level where you just try to naively apply the rules of quantum field theory, and you get infinities you can't deal with. There are infinities in all quantum field theories, but some of them you can sweep under the rug very easily. Those are called renormalizable theories. Gravity is not a renormalizable theory. It has further problems. So over the last 2 or 3 decades, people have started to work on an alternative to quantum field theory, which is premised on a very simple starting assumption, which is just that rather than point-like particles, you assume that the objects moving around are little loops of string. They're little one-dimensional objects. And if you make that assumption, you change the picture of space-time where a point-like particle will move along and emit a photon. That's an electron emitting a photon, which then connects to another electron. In place of that, you get a picture where 2 loops of string will interact by sending a loop of string across. This gives you a smooth picture of how strings interact. And that smoothness of the picture on the right compared to the picture on the left is what makes it a much better behaved theory in some sense. So if we just do this simple technical thing, we replace point-like particles with little loops of string, we discover that we automatically get a quantum field theory which has forces like electromagnetism, but it also has gravity in it. It just pops out automatically. So that's great. I think we're definitely on the right track. The biggest catch here is that this theory lives most naturally in 10 space-time dimensions. So if you think that this is the right theory describing quantum gravity, and right now it is really the only consistent and robust framework we have to describe quantum gravity in a higher number of space-time dimensions and its variance, you're stuck dealing with 10 space-time dimensions. So how do we deal with that? Well, there's a notion which people have pursued for many years, which is called compactification. And basically the idea is maybe not all the dimensions of those 10 dimensions are big. Maybe you can get rid of 6 of them by curling them up into some very small dimensions. Like imagine a very long straw. If you look at a very long straw from a ways away, it just looks like a line. Actually, the surface of the straw is two-dimensional. It's curled up in a little cylinder, but if you're far enough away, you don't notice that. So we may be living in a space-time which is really 10-dimensional, but we're only seeing 4 of those dimensions. The other 6 are curled up very small. And the structure of those extra 6 dimensions, depending on exactly how you curl them up, can give you different kinds of quantum field theories. That is, it can give you electromagnetism and the strong and weak nuclear forces, or it can give you things which are slightly different. And that's where we're going to get to this issue that there's lots of different solutions. Yes, question? Good. So the question is whether there's a natural reason for the dimensions to curl up like that. There are a number of suggestions, and it's obviously very attractive to try to find a reason why we would live in 4 dimensions rather than a different number of dimensions. I would say at this time, none of them are really convincing. I mean, there are some notions that there are extended objects that might wrap around some of these dimensions, and they would kind of keep some of them from expanding and allow others to expand. And there's some numerology that might make that a plausible story, but I would not say that it's yet a really robust story. So in particular, you can already see that the number of dimensions of space-time that we observe is not obviously predicted by string theory. So in some of those other regions I mentioned, the apparent dimension of space-time may be different, right? If you go far enough away, our next-door neighbors in the next patch may have a 6-dimensional apparent universe. That's one of the things that might be different. One of the other things that might be different is they might have a different compactification. They might be compactified down to 4 dimensions on a different manifold, which would give some other quantum field theory. So you can start to see how you're going to get a lot of different solutions. Okay, so an important question is string theory a unique theory? So there's a famous parable of the Indian parable of the blind man and the elephant, which people like to trot out at this time, so I will trot it out. Here's the elephant. You have a bunch of different blind men, and there's an elephant, and each one of them approaches the elephant and touches a different part of the elephant, and one of them describes it as being sort of hard and smooth because they were touching the toenail, and one of them describes it as being kind of like a snake because they were touching the trunk. Anyway, string theory is a little bit like that. For a long time, we thought there were 5 different string theories, and they have these names you can see up here: type 2A, type 2B, heterotic, SO32, et cetera. I've got 6, and I'll mention that in a minute. What was realized about 10 years ago is that these are all different pieces of the same underlying structure. There are things called duality symmetries, which relate all these and show that they're really all part of one underlying mathematical framework. They're all limits of the same theory. So string theory is, in fact, unique. Not only that, but there's another thing over there called M theory, which is not even quite a string theory. It's 11-dimensional rather than 10, and it doesn't have strings at all. It's got 2-dimensional membranes. It's also tied into this thing. So there is some underlying mathematical thing. We can't quite define it, but we know how to define certain limits of it. And the limits of it that we can define are the little pieces of that elephant that the blind men have been touching. So string theory is a unique theory. It's got some unique underlying mathematical structure, even though we can't articulate it yet. But it has many different realizations in terms of the kind of physics you can see coming out of it. That comes from the fact that there are many different compactifications, many ways of curling up those extra dimensions, and each one of those can give you different kinds of physics in space-time. So that leads us to the vacuum problem, which is what I started discussing at the beginning. So until about 5 years ago, if you asked most people that thought about these things, they would have told you, well, the cosmological constant is almost certainly 0, and it seems like there's lots of compactifications of string theory, but there's probably some mechanism which just forces it to choose one. So when we really understand the theory, we'll probably have some dynamics which will force us into one particular vacuum. It will have lambda equals 0. That will be the world, and we'll be able to predict the mass of the electron. There was a quote, I don't know, 20 years ago, 15 years ago, by an outstanding physicist who commented that, well, it seems like it's now only a matter of technical details before we can predict the mass of the electron to 20 digits, something to that effect. Hasn't been done yet, and it's now not quite so clear that we will be able to do that for the following reason. As we've discussed, experimentally it's been observed that the cosmological constant is not 0, it's 10 to the minus 120. And in a parallel development, not necessarily related to that, but certainly the idea of looking for solutions with positive lambda has been has been promoted quite a bit by this observation, it's been realized that in string theory, we really don't have a natural mechanism to pick up one vacuum. There's many, many solutions with lambda equals 0, and there's many, many solutions, it seems, with lambda not equal to 0. It's harder to mathematically characterize the ones with lambda not equal to 0. But in fact, we can show that there are an infinite number of solutions to string theory, each of which gives you a different local space-time physics. Now, if you put in some really simple cutoffs, like that the size of the compactification manifold is not too big, so we would have seen it already, then you can cut it down to a finite number that we can actually compute. It's not to say that there has to be a finite number, but the ones we know about are on the order of 10 to the 1,000, it seems, from basically putting together a bunch of pieces people understand and making the most natural conclusion. So there are an enormous number of different ways of using string theory, compactifying it, and coming up with some kind of four-dimensional physics like ours, but different. And that number starts to be on the order of 10 to the 1,000. So is this, yes, please, question. These are, okay, so the question was, is there any notion that some of these solutions might be more likely or more stable? And those are precisely the questions that a lot of string theorists are trying very hard to answer right now. You can waive your, so let me address those two things separately. One is the likelihood. The likelihood would involve choosing some kind of a measure, a distribution on the space of these vacua. And to do that, we would really have to understand the dynamics of the theory and the dynamics of quantum gravity better than we do. This picture of inflation with this kind of tunneling process that I talked about is something people do not mathematically understand very well. And in fact, it's very hard to assign probabilities. There's a sense in which we really have no idea how to define probabilities for these things because you get an infinite number of things at some point. And it's like if I give you all the integers and I ask you what fraction of the integers are even, your natural response is half, right? But then I can list them in a very different way. I can, list uneven integers every third, 1, 3, 2, 5, 7, 4, et cetera. And I would say, well, only a third of them are even. It really depends on what you put in as a cutoff, basically. So we don't know how to do that. There may be a sense in which that's true, but we don't have the mathematics to describe it yet. Right now, all we can do is talk about the solutions. The second question is whether some of them can be stable and others can be unstable. That is probably the most promising way in which to get rid of this rather disturbing picture I'm painting where there's so many solutions. It is possible that many of the solutions are unstable. All the solutions with positive cosmological constant are probably unstable, but on a very long time scale. Time scale is much, much longer than the history of our universe. In particular, if you have a small cosmological constant, you can always decay into an even smaller cosmological constant, but it takes a long time. On the other hand, if your cosmological constant is 1/2 in natural units, and there's a nearby vacuum with a cosmological constant of 1/4, you're going to be unstable to that vacuum in a very short period of time. So there is a sense in which that instability will naturally take you down further and further to smaller cosmological constants eventually. I hope that answers your question. Okay, so is this picture at all sensible? I mean, should we take this at all seriously? This is sounding pretty wacky. We're talking about an enormous universe with different regions that we can't really observe. Why would we really take this seriously? So there's a kind of a prescient argument by a Nobel Prize-winning physicist named Steven Weinberg, who made an argument which I think is one of the more compelling arguments for taking this story seriously. And his argument was as follows. Before anybody had observed that there was a non-zero cosmological constant, he did a little calculation. He said, if the cosmological constant was bigger than a certain value, remember the cosmological constant causes things to move apart from each other. If it was bigger than a certain value, then before galaxies had a time to form, everything would have just drifted apart or been pushed apart by the cosmological constant. Galaxies would never have formed. We would not have the kind of nice structure we see in our patch of the universe, and we would probably not be here. And he computed the number, and the number was 10 to the minus 118. So if the cosmological constant was bigger than 10 to the minus 118, then we wouldn't be here because galaxies would never have formed, structure of the kind we see would not have formed, and we would just have a diffuse gas of particles moving apart from one another. Or at least we might have smaller structures, but nothing as big as what we need to get our kind of structure in the universe. So he made this argument before anybody measured that the cosmological constant was 10 to the minus 120. And then people measured that, yes, it's just below his bound. It's 10 to the minus 120. To me, that's actually a kind of a compelling observation because it says that if this story is correct, that there's a lot of different patches with different cosmological constants, then the fact that we live in the patch with 10 to the minus 120 is just kind of an environmental feature of the fact that stuff like what we see can only occur in certain places in the universe. You don't ask the following question. You don't look around and say, look, most of the universe is empty space. Why are we not sitting in empty space right now? I mean, statistically, we should be in empty space, right? That does, you don't even have that discussion, because it's clear that for us to be here, we would have to be living in a patch where there's a bunch of mass and a planet and all that stuff. In the same way, it may be that the universe is very big, and we're not in one of these other patches for the same reason we're not in empty space, because nothing interesting happens there. So to me, this is actually a somewhat compelling argument. It certainly makes us, it certainly is one which indicates that we should perhaps take this point of view seriously and at least try to debunk it. So the picture we've assembled by this time is often referred to as the string landscape. Is one of your neighbors at Stanford University here, who I've been talking to a lot this semester and last few years, is a guy named Lenny Susskind. He recently wrote a nice book, which I recommend to anybody interested in learning a little bit more about this, called The Cosmic Landscape. He, I think, was at least partly instrumental in coining the term the landscape to describe this scenario. Basically, the picture we end up with is a landscape where there are lots of hills and valleys in this cosmological constant scattered over the space of possible string configurations. And there's a bunch of local minima denoted by the green points. And the different minima correspond to different kinds of vacua. The lake there is a continuous many-parameter family of vacua with lambda equals 0. And the various local hills are things with lambda maybe greater than 0, but some of them will have lambda less than 0. But there could be lots of these. If there are enough of these, in particular, if there are greater than 10 to the 120 of these, and if lambda is relatively uniformly distributed between 0 and 1 or -1 and 1, then generically, just by probability, some of these vacua will have 10 to the -120 or smaller for their cosmological constant. So in fact, the best way to realize a vacuum which has such a small cosmological constant is to just have a whole bunch of them, and have some of them, just by random statistics, have to be small. Otherwise, you have to somehow fine-tune nature. So in some sense, it's the simplest explanation for how to get a small cosmological constant. It's just that there's so many different possibilities, we just happen to have enough possibilities that we get some naturally. So you're actually naturally led, in the absence of some kind of really detailed fine-tuning of how the universe works, to a picture where there are lots of different vacua, and most of them don't have such a small cosmological constant. Okay, so what this leads to, if we put this in the context of this inflation and bubbling story that we talked about, is now we have this potential, and if you're sitting in one vacuum, say vacuum 1, which is the red vacuum, there's always a possibility that some little patch of the universe will bubble up a patch by quantum tunneling that's in phase 2, in the second of these vacua. Phase 1 will expand, because when you have a cosmological constant, space expands at an exponential rate. Phase 2 will also expand. So the amount of space that is in each of these two phases will expand exponentially. The amount of space in phase 1 will expand faster than the amount of space in phase 2, but they'll both expand exponentially. And then if there's a region 3, we can either tunnel from 1 to 3 or from 2 to 3, and we'll get patches of 3 appearing inside the patches of 1 and 2. And if you go on from 3 to 10 to the 1,000, you get some idea what the picture of the universe might look like. There might be regions which are in one phase with bubbles that are in another phase, containing bubbles in another phase, up to 10 to the 1,000 different kinds of phases, all scattered around the universe. Okay, so that's the picture we end up with. Now, the question I want to address is, if that's the universe, then what do we do about it, and what can we actually do in terms of carrying out the goal of physics, which is to actually make predictions or figure out how to explain the physics where we are? So the vacuum problem is, where are we in this picture? Yes, question. There would actually be boundaries separating these regions. It might be hard to get to those boundaries, because if you're in a given patch, because of the fact that the universe is expanding, things that are distant are moving away faster and faster. So for instance, if we live in a patch with our cosmological constant that we've observed, because of this accelerated expansion of the universe, if you started traveling at the speed of light out towards the boundary of the universe, by the time you got there, it would have moved so far away that you would just have to keep going and going, and you would in fact never be able to reach the things which are past a certain point called the Hubble radius. So we can't actually get there, but there may be a boundary out there. If you had a global picture of the space-time, then you would have a function where you would be living in one vacuum, and then there would be some kind of a kink where the thing would move into another vacuum, and then you'd be living in the other vacuum. So there would be boundaries, domain walls separating these different kinds of physics. But unless you were lucky, you wouldn't be living in a region where you could see one. But yeah, there was another question?
So to an extent, there's some boundary might be heading towards us right now.
So the question is it possible that there's a boundary heading towards us at the speed of light? And yes, it is possible. It is not required because in our patch of the universe has this Hubble size. Anything that happens outside the Hubble size will never get into us. Now, it's possible that out at Alpha Centauri, it might happen that a little patch of another vacuum forms, which is just big enough in some next, maybe we're in vacuum 2. Maybe a patch of vacuum 3 could form somewhere out there, and it would expand fast enough. It's close enough to us, and it's expanding fast enough that we would not get away from that. It would just come and hit us. So it is possible. It's very unlikely because we have such a small cosmological constant that probably the time for the decay is at least billions of years or much longer. But it is not logically impossible in this picture. Yes, another question.
Would these patches of vacuum be observable for dimensional space, or how would that be?
Well, this is where you get into, okay, so I should add here that a lot of physicists really hate this picture. And there's a lot of controversy about whether it makes sense to talk about this, what you do with this picture if it's right, or really whether this is physics. Because when we talk about one of these other patches, we are in principle unable to move to one of those other patches and measure things. In our patch of the universe, even if there's 30 billion light years away, there's a domain wall, we'll never see it because it's outside our Hubble radius. So parts of this are very hard to verify directly. Now, there are other things in physics that are hard to verify directly. Nobody's ever seen a lone quark, and yet we believe that there are quarks. Quarks come in sets of 2 or 3 that are tied up in little bundles which have no charge under the strong nuclear force. The fact that nobody's ever seen a quark doesn't make people not believe it. It just means you have to have more sophisticated indirect evidence that this is true. Now, I believe that if we can get string theory to the point where we can say, look, this is a really robust theory, this is what it predicts, and it also predicts the following things which we can verify by experiment, then we will be in a situation where we have to believe that this is the simplest explanation for our universe, and therefore this is probably correct. But we may never be able to measure those things directly. Yes, other question.
Is there any preference when you tunnel from one patch to another, whether you're increasing or decreasing?
Good, so the question is there a preference when you're tunneling from one vacuum to another, whether you're increasing or decreasing lambda? Now, the process of decreasing lambda is called a Coleman dilution instanton, and it's been fairly well understood in physics. It is pretty straightforward to construct a sort of a solution in a certain Euclideanized version. I mean, there's some technical stuff you have to do, but there's a relatively robust sense in which people think they can make sense of the tunneling from a higher cosmological constant to a lower one. There is some controversy, I would say, as to whether you can go up. I don't think there's universal agreement on that. The general feeling, I think, is you probably can't, but I would not want to go out on a limb on that one. It's a harder thing to understand.
So there's not a direct relationship between the energy and
I'm sorry, the dark energy is proportional to lambda.
Yeah, but I mean, when you're looking at the energy.
Yeah, the trick about quantum mechanics is for short periods of time, you can tunnel into things with higher energies. Right? You can disobey conservation laws for very short periods of time in quantum mechanics. And we don't understand quantum gravity well enough to know whether if you momentarily disobey the law of conservation of energy by formulating a little bubble of more energy, that thing is going to start inflating under its own cosmological constant. It will just keep on going. We don't understand whether you're allowed to do that or not. Another question.
I just want to warn you that it's not a secret plan.
Okay, I have 9 minutes. I will, I think, conclude in 9 minutes. Thank you very much. So the problem is, where are we? So this leads to the last part of my talk, which is actually the computational challenge here of, is this something where we might hope to make some progress in terms of figuring out how we could make a prediction, even if this outlandish paradigm is correct? So there are 2 things that we can try to do, which I think will help us to move towards making physical predictions. The first thing, obviously, is to try to identify our vacuum. Right? Which vacuum do we live in out of these 10 to the 1,000? That's a hard problem because you have to look at a lot of different vacua. A simpler thing you might try to do is to try to find structure in this landscape. You might try to find, for instance, things which are always correlated. That is, if you find one feature in the landscape, in all vacua, if you find that all vacua with a particular feature also have some other feature, and we have the first feature in our world, then you might hope to find the second feature. But there is this issue, which is that even if we know the theory and we can mathematically write it down and we can compute precisely each of the vacua one at a time, although we obviously can't run through all of them because we don't have enough particles in the universe to do it, if we could in some way compute each of them, if all the observables are uniformly distributed and independent, then we are in trouble because we may not be able to make predictions, right? If there's other versions of the universe right next door which could have any possible imaginable value of the electron mass, of the fine structure constant governing the strength of electromagnetism, if all these things can be tuned to arbitrary precision by just choosing some vacuum, we have far less than 1,000 digits of experimental information that goes into our characterization of the standard model of particle physics right now. We could presumably dial each of those parameters arbitrarily if all these things are uniformly and independently distributed. So there's kind of a semi-organized effort going on. I mean, it's basically just a bunch of people doing their own individual things, but there's some effort to organize this a little bit. Mike Douglas from Rutgers, Gordy Kane from Michigan, myself from MIT, lots of other good physicists from some of the best institutions around, both here and in Europe, are thinking about this. And we'll mention it's sort of skewed towards the younger end of the age distribution. A lot of the older physicists are more skeptical of this approach to understanding physics, and this controversy is kind of an interesting sociological phenomenon. But there's also sort of an East Coast, West Coast split on this one. I'm one of the renegades on the East Coast who's more into this. But anyway, lots of people, both here and in Europe, are working to try to analyze these vacua. And what we need to do is, there's a number of steps that have to be gone through. We need a mathematical formulation of the problem. And we don't actually have a complete mathematical definition of string theory yet, so we need to work towards that. But along the way, we can characterize these vacua fairly well in many cases without even knowing how to define the theory, which may sound difficult, but it's true. Once we can mathematically characterize the problem, we need to come up with efficient algorithms. You're all familiar with that issue. You have some mathematical framework that's in some paper somewhere, and you have to figure out how to make an efficient algorithm to actually solve the problem. And then once you know what the algorithm is, you have to actually perform a systematic search involving implementing the algorithm, putting it on a bunch of computers or a computer, and running through things. And then you get a whole bunch of numbers out, and you have to interpret those results and say, does this tell us anything about physics? So each of these 4 steps, I think, is a major challenge, and there's interesting things to do on all of these. I think of particular interest, perhaps, to the people here, there are a lot of challenging questions having to do with algorithms and systematic searches, which really form a major computational challenge here. We're obviously not going to search through 10 to the 1,000 vacua by just having a computer run through them one at a time, because we'd never get there. We need to be smart about how to do that. So yeah, I got about 5 minutes, so I'll just whip through this. Let me just give you a little bit of a sense of how you construct different vacua. So the first thing you do is you have to pick a 6 or 7 dimensional manifold on which to compactify things. One class of manifolds which people have compactified on are called Calabi-Yau manifolds. They're certain mathematical gadgets that we can characterize by certain combinatorial data in certain cases in a very simple way. One of the first computational efforts in this direction was done by Kreutzer and Skarka. If you Google Kreutzer and Skarka and Calabi-Yau, you will find their online searchable database of 473 million Calabi-Yau manifolds. So there you can just get a little sample of a tiny fraction of the number of possible string compactifications. These are 473 million different things you could compactify on. Each one will give you different physics. There are probably many more Calabi-Yaus. Nobody even knows if the number is finite or not, but certainly this is probably a small subset. But it's a nice subset which is easy to characterize. There are also other spaces possible, and even spaces which are not really geometric, but I don't have time to get into that. Generally, these Calabi-Yaus will live in the lakes in that landscape. They will have lambda equals 0, and they will have continuous moduli. Like if you take a circle, the circle could have an arbitrary radius. The simplest string compactification is you compactify on a circle, and then you're in 9-dimensional space-time. That circle can have arbitrary radius. That will change the coupling constants in the 9-dimensional theory. You want to get rid of these things which are called moduli, which are those parameters. So you put in some things called fluxes, which are like generalizations of electromagnetic fluxes. And when you put in those fluxes, you generate the landscape I described, where you have lots of isolated vacua. So there's been some progress in classifying these different so-called flux vacua. If you combine Calabi-Yau manifolds with fluxes, in principle, this gives you a compactification with a certain
with a certain cosmological constant. Now there's a real trick, which is that nobody can calculate the cosmological constant in a case where it's non-zero for any of these vacua. And the reason is the cosmological constant is the energy density, which comes from summing up a huge number of terms, which are like +1, -1, +7, +0.7, -0.3, et cetera. A whole bunch of numbers with opposite signs, and these things have to add up and cancel to 0 to within 120 decimal places to get 10 to the minus 120. It's really hard to compute those things. We don't even have mathematically the formalism to do it, but even if we could, there was a nice argument by Denef and Douglas, which shows that even in the simple models, the problem of finding a vacuum with a small lambda, even given some simple models for how to compute it, is an NP-hard problem. It's a lot like the minimal length vector problem. You know, this problem where if you're given vector, you're given a set of vectors in a space, and the question is, what's the integral linear combination of those vectors of the shortest length? That's an NP-hard problem. And that is at least the cosmological constant problem, even in the very simplest cartoon characterization, is at least that hard. So even if somebody could write down all the models and then ask you to calculate the cosmological constants, it would be very hard to locate our vacuum with 10 to the minus 120 cosmological constant. Okay, so you might worry at this point and say we're totally out of luck. It is true that because of this mathematical and computational complexity of the cosmological constant, it may be intractable to identify our precise vacuum, or even to compute those vacua which have such a small cosmological constant. But that is not the end of the story. I would say that all is not lost. If, in fact, the cosmological constant is relatively independent of other features, we may be able to predict everything else about physics and just not the cosmological constant. And then we would just have to say, look, we found 10 to the 400 vacua with all these properties. The cosmological constant is uniformly distributed. One of them must be ours and have a small cosmological constant. So if we can show that all models with particular features, let's say features X and Y, which are observed in nature, also have some other feature Z, then we can make a prediction. We can say if you do a particle accelerator experiment which should measure Z, we should see it because every model we found in string theory has that. That would be a prediction out of string theory even in the face of this computational complexity. So to do that, what we have to do is we have to look for correlations in the landscape. So then we have various different ways of getting into more detail. Now we have to not only have a compactification, but we have to pick the forces of nature and the particles. And there's one way to do this, which is by putting higher dimensional things called branes. I won't get too much into this, but we can put in things wrapping the thing we're compactifying on, and they intersect in certain places, and the way that they intersect will give rise to some number of quarks and some number of electrons and things like that. So skipping a lot of the complexity, we can formulate this problem essentially as a partition problem. Given a big vector, we're given a bunch of little vectors, and the question is, how many ways are there of adding up an integral linear combination of the little vectors to get the big vector? So in this case, the integers will correspond to the forces of nature. If n equals 1, it's E and M. If it's 2, it's the weak force. If it's 3, it's the strong force. If it's 4, it's something we don't have in our part of the universe. So there's a partition problem. If we want to evaluate all partitions, you can think about that as a computational problem. It's an exponentially hard problem. There's an exponentially large number of solutions if there's lots of solutions. A group in Germany, Blumenhagen et al., spent a year on computer time computing through all these. In some recent work with Mike Douglas, we've been doing this, but we took a different approach. We basically are just looking for the class of models which include the standard model. So we're saying, look, if you fix the standard model, the partition problem becomes a cubic time problem. So actually in the last couple of months, we put it on a computer, we've got a bunch of algorithms, and we can show that in this particular class of models, there's only on the order of 10 to the 7th or 10 to the 8th, which have the standard model gauge group, and of those, only about 10 have the right set of particles. Now, this is only a piece of this landscape, but it's an example of how by using computational cleverness, we can actually start to find data sets of vacua which we might compare to our universe. Summary is the universe may be very big, really, really big, as many zeros as you can imagine. Physics in other places may be very, very different from the physics we have here. String theory seems to have a lot of different solutions and can describe many of these solutions, but there's a real challenge in figuring out how to make predictions based on this model. And I think not only are there mathematical, but also many computational challenges. And I think it's pretty interesting. It's a place where mathematics and physics and computer science all kind of come together. We want to do a bunch of searches. And so I hope you found this amusing. And if any of you are really interested, I can give you more references, or if you want to spend some of your 10% time trying to find vacua, I'd be happy to talk to you about that. I'll leave it at that.